Welcome to the video on odd and even functions. Let's go over what the concept of an odd and even function is. We'll start with even. The best way to see what an even function is to look at an example. An even function is one where when you have opposite inputs, you have the same output. I'll show you what I mean by that. Suppose we were to plug both 5 and negative 5 into our function f. Well, it turns out, if we do that, we get the same result. Hit pause if you want to see the particular algebra. The point is, when you plug in opposites, 5 and negative 5, you get the exact same result. To be more specific, an even function is one where that result happens every time you plug in opposites, not just if it happens to happen once. Now, a more formal definition of an even function is this. I'll pause while you read it. And while these definitions may sound drastically different, they really say exactly the same thing. We'll dispense with the formal definition for the moment. Now let's take a look at what an odd function is. Here's an example of an odd function. An odd function is one where when you plug in opposites, every time you get opposite outputs. I'll show you what I mean by that. Notice in this case, we've plugged 4 and negative 4, two opposite numbers, into our function g. Well, I did all the algebra, and you can hit pause if you want to see it. But the point is, we plugged in opposite inputs, 4 and negative 4, and we got opposite outputs. Negative 104 and 104 are opposites of each other. Now, this could happen coincidentally in a particular function, but if this were to happen every time we plugged in opposites, then we would say that that was an odd function. Here's a more formal definition of an odd function. I'll pause while you think about that. We'll dispense with the more formal definition for the moment. So this brings up an interesting question. Can a function be neither odd nor even? Yes, as it turns out. Here's an example of a function that's neither odd nor even. Here's how we know it's neither. Watch here as I've plugged in opposites, in this case 2 and negative 2, into the same function. After doing all the algebra, hit pause to see the particulars if you'd like. After doing all the algebra, we neither get identical outputs nor opposite outputs. They may be opposite sign, but they're not literally opposites like 6 and negative 6 or 10 and negative 10. And so this function doesn't meet the definition of odd, and it doesn't meet the definition of even. So not all functions, in fact, I would say most functions, are neither odd nor even. Now let's take a look at how we could prove that a function is either odd or even. Here are informal definitions again. Let's take a look at an even function first. Suppose I wanted to prove that this was an even function, which it is, by the way. Well, I have to prove that every time I plug in opposites, I get the same output. How do I prove that something happens every time? What if I plugged in 1,000 numbers and their opposites, and in each pair, I got the same result? That wouldn't prove that it happened every time. That would just prove that it happened 1,000 times. So to prove that it happens every time, we pick a symbol to represent any particular number. Let's use the letter C. And what we do is we plug in C and its opposite, negative C. By the way, on the algebra on the right, if I could just remind you about the negative c quantity squared, that means this, which means this, which means that, or just c squared. And so the expression on the right simplifies to this. Well, I haven't actually plugged in a specific number into my function f, have I? But I have plugged in c and negative c. And the algebra shows that I get the same result when I plug in opposites. And therefore, these two quantities are equal every number I could plug in, because c represented any possible number. And that meets the condition that proves that the function is even. Now let's take a look at an example of proving that a function is odd. Here's a particular function. It turns out to be an odd function. Suppose we wanted to prove it. Well, we would have to prove that anytime we plugged in a number and its opposite, that the answers were always opposites. Well, to prove that that happens every time, we're going to consider the symbol c to represent any particular number, and I'm going to plug c into my function and negative c into my function. Now let's work out the algebra that's on the right side of your screen. Just a reminder for the negative c cubed portion, negative c quantity cubed means negative c times negative c times negative c, which means this. Negative 1 times negative 1 times negative 1 is negative 1. And therefore, this works out to negative 1c cubed. Well, what that means is that this expression in the box here is equivalent to this. And therefore, this expression simplifies to that. I'll pause while you convince yourself of the algebra. So weren't we trying to prove that if we plugged in any number and its opposite, that we got opposite results? Well, look at the two results that we got. They are opposites of each other. Isn't it true, after all, that negative 1 times the quantity on the right equals the quantity on the left? This is an important fact. I'll stop talking for a minute while you read and convince yourself that that's the case. If negative 1 times some quantity equals another quantity, then those quantities are opposites by definition. And therefore, when we plugged in c and negative c, we did in fact prove that negative 1 times f of negative c is f of c. In other words, we proved this, which is the same as showing that the functions are opposite. It could be written this way as well. Now, aside from proving that functions are opposites, odd or even, there's the issue of graphic symmetry. Let's take a look at an even function graph. This function has a certain symmetry to it, as you can see. And what makes it even? Well, without any algebra, we can see graphically that this is an even function. Here's the symmetric interpretation of what the graph of an even function looks like. It has what's called y-axis symmetry, which is the geometric way of representing the definition of an even function. And so, for example, if this graph were to pass through 4, 1, it would also pass through the mirror image through the y-axis, negative 4, 1. But isn't this the same as we plugged in opposites, 4 and negative 4, and got the same result, 1 in each case? And just to give you another image of y-axis symmetry, this is a point on the graph. What are its numerical coordinates? Well, let's not concern ourselves with that. But if you have a random point on the graph and its mirror image is also on the graph, then you can say that those 2 points are symmetric through the y-axis. And if that happens for any pair of points, such as here and here, then it's fair to say that because of the overall y-axis symmetry of this function, whatever its algebraic equation may be, we don't know, this function is even. Here's what an odd function looks like in a symmetry sense. Here's an example. This function has something called origin symmetry and conforms to the definition of an odd function. Here's an example. This particular graph happens to pass through 3, 2, but it also passes through the point -3, -2. Now these points are called symmetric through the origin because if you were to draw a line from one dot to the other, it would go through the origin and the points are equidistant from the origin. They essentially reflect through the origin. Think of it another way. Here we plugged in opposites, -3 and 3, and we got out opposites, -2 and 2. And if this were to happen every time, which it would in this diagram, then the function would be odd. For example, here's a random point on the graph. Try to visualize where its mirror image through the origin would be. If you thought up here, you're right. And if we were to pick another point on the graph, its mirror image through the origin would also be on the graph. And because this happens for any chosen point, this is an odd function. And that completes the lesson on even and odd functions.